All right, so we have another question about caches. In order to solve this question, I'd like to first introduce the cache to you. This is the cache we're talking about. It's just a portion of the cache is illustrated in this table. So the question says this cache represents a two-way set associative cache. In other words, there are two lines per set, and we have the set ID values which start from at this particular address point here. And we increment this number every other row. That means these two rows, for example, are the same line in a given set. So we've got another two rows, another two rows. So these are like two rows, next to each other, and then another two rows next to each other, etc. Okay, so that's how. So these are the first set, and this is my second set. Okay. Again, as I said, there are it's as it is illustrated. There are 14 bits for the tag values and 8 bits for the set ID here, and there are 2 bits for the word ID. As you can see, those numbers at these word positions are bytes. So this in this particular cache is word is defined to be 1 byte. Okay, so it's just a special case. Word could be 2 bytes, 4 bytes, etc. But in this particular case, it's 1 byte. And so there are 2 bits used for the word differentiation. So we got 3 questions for this particular cache. The first question is, let's suppose that we have a load word instruction coming in from the CPU with the following address. The address is given by 7121C5, let's suppose, okay, and that's hexadecimal, all right, in hex notation. Sometimes we put 0 and x on top of this number to illustrate this particular number to belong to a 16 number system, base 16. Okay, so what is the data value that is stored in this particular address location, right? So in order to determine that, we have to first translate this number to binary. And it's pretty easy because we do digit by digit. 7 is given by 0, 1, 1, 1, right? And then 1 is given by 0, 0, 0, 1. And then 2 is given by 0, 0, 1, 0, right? And then 1 again, 0, 0, 0, 1. And then we have C. C is given by 1, 1, 0, 0, and then finally we have 0, 1, 0, 1, which is 5. Okay, this is 5, this is C, blah blah. So, which means we actually translate it into 1, 2, 3, 4, 5, 6, 6 multiplied by 4, 24 bits long, okay, address. So in this case, we translated it to binary 2. So now we have to look at what the tag value is, what the set ID is, and then what the word. For example, the first thing that we identify is 0, 1. So that means we're in the second row, okay? Because that's where the word address matches with this. And then in the next 8 numbers and 8 digits, 1, 2, 3, 4, 5, 6, 7, 8. So this section, okay, is the set ID value, and it turns out that this number is actually here, okay. It's the set ID value that we have a matching circuit that determines exactly these addresses. And finally, we have the tag number, and this tag number matches this particular one, okay, which means we're looking for this particular data value, which is A5. So the answer is A5 for the first question. Okay, so this A5 is going to be loaded up to one of the registers of the CPU, and load word instruction will be over. All right. Anyway, let's go to the second question. Second question is simply saying how many lines are there in this cache. It's pretty simple because you can see that there are 256. This is two-way set associated cache. So there are two-way. That means there are 2 sets, and each set has 256 lines. Why? Because it's 2 to the 8. You remember there are 8 bits used for the set ID. Okay, so there are 8 bits used. So 2 to the 8 makes it 2 to the 56. And, I'm sorry, 256 multiplied by 2 because we got 2 sets, so which gives 512 lines, okay, or cache lines. Okay. And finally, the third question we have is the following. How many blocks are contained in the memory space of the cache system defined on this table? Well, you can see this is asking for blocks, but we could have been asked, for example, how many bytes of memory can be supported with this cache system. This could be another alternative question. So it's pretty easy because we have 14 bits used for the tag and 8 bits used for the set IDs, so which makes it 22. So that's the most significant 22 bits in here, and the rest are just words, right? So which means we have 2 to the 22 blocks, okay, or cache blocks, okay, and each block has you can actually put 4 different words in that block, and which word it is determined by the last 2 bits of information. If I ask you how many bytes can be supported within this cache system, then you would say 2 to the 24 bytes, okay, which would be 2 to the 4 multiplied 2 to the 20, and 2 to the 20 is megabytes, so which means 16 megabytes can be supported by this cache system. Okay.